Confidence intervals are one of the foundational concepts of statistics. You might see them in academic journals, in forest plots, funnel plots, bar charts. They're everywhere, but how are they actually constructed? And why do we need them? Well, in this video, we're going to be exploring all of those concepts and more. My name is Justin Zeltzer, and this is zedstatistics.com. Now, this video forms part of a series on the foundational concepts of health statistics. And if you want to see any of the other videos, you can check out the link in the description below. I'll put a link to the playlist. But you can see all my videos up on zedstatistics.com. And as always, if you like the video, give us a thumbs up, subscribe and do all that stuff. That'll help me out a ton. Otherwise, let's jump straight into confidence intervals, shall we? Alright, so the first thing I'm going to do is work on your intuition around confidence intervals. I'm trying to do it without any mathematical formula. We're going to move on then to an actual calculation of confidence intervals. And we're going to be looking at two particular intervals that are commonly created. One which is created for a population mean, and the other which is created for a population proportion. From there, we'll have a look at some other examples of confidence intervals you might see in the wild. And finally, I've got this sealed section just for the stats nerds out there, or even if you're not a stats nerd, you can come along. We're going to have a quick look at the difference between frequentist and Bayesian intervals. But let's jump straight into the intuition now. So the first thing we need to understand is that statistics is about estimation. That's a crucial point to get your head around confidence intervals. So here's the example I'm going to be using. We want to know what the average resting heart rate is for women. So if I was to ask you how you'd find the average resting heart rate for women, you might say, well, look, Justin, I need to take a sample. So here we have a sample of 5 women, that's n equals 5. And these are the heart rates for each of the 5 women. And we can find what's called a sample mean, which is in this case 79. Now the symbol x bar is often used for the sample mean, but appreciate that if we took another sample, we might get 5 completely different values. Now these would be beats per minute, just by the way. And of course then we'd get a different sample mean. So it's not as if this sample mean is the end of the story, right? And realistically, what this is an estimate for the true average heart rate for women. And when I say true, I'm talking about what we might call the population mean or the population average. So we could use this 79 we got from our sample mean and hopefully construct a kind of interval where we go, all right, we've got 79, but we know that it's just a random sample. Maybe the next sample might be 77. Maybe the next sample might be 85. Who knows? But this does tell us something about the population mean, doesn't it? In that we know the population mean's not going to be something like 40, right? And we also know it's not going to be something like 120. Well, it's very unlikely to be those two numbers looking at the sample we've been given. So we got some kind of information about the population mean, but what we want to try to do is give us what's called a confidence interval. So we might be able to say something like this. We are 95% confident that the population mean, mu, lies between, let's just say, 67 and 91. Now you'll notice that the sample mean lies right in the middle of this interval. And that actually tends to be the case for most confidence intervals we'll be creating. Because realistically, there's no reason to think that the population mean should be specifically higher or lower than this sample mean we've got. So it should be nice and balanced, this confidence interval, around the center of the sample mean being 79. So you may well be asking now, why is this 67 and 91 specifically? How did we calculate those two numbers? I get that 79 should be in the middle, but how wide should this confidence interval be? And why did we choose 95% confidence? Well, let's go and have a look at how confidence intervals are calculated. So as I said before, we were looking at two different confidence intervals. One where we're doing a confidence interval for the population mean, And another way we're doing it for a population proportion. Now they're just different types of data that's going to give us either a mean or a proportion. And for example, we saw before a potential population mean when we were estimating the average resting heart rate for women, because that will be in beats per minute. And a population proportion might be something like this. What proportion of women have high heart rates? And let's just say a high heart rate is at least 100 BPM. But you can see we actually have what's called binary data on this side. We've got just a collection of yeses and nos, right? Either you do have a high heart rate or you don't. And on this side, on the mean side, we actually have numerical values for the heart rates. So on the population mean side, we're trying to estimate mu, which is the population mean, using x bar, which is our sample mean. And on the proportion side, we want to estimate pi. Now that is the Greek symbol we tend to use for population proportions, and p is going to be our sample proportion. Be aware that you might also see the Greek letter theta used in either of these two scenarios for a general population parameter. Okay, so what we're trying to aim to do is use our sample mean, wherever that happens to be, and then construct for ourselves this interval for the population mean. Similarly, we can use the sample proportion and construct this population proportion interval. So I've actually created some data for this, which you can, if you go to zedstatistics.com, you can download this if you want to have a play around yourself, that is. But it's basically 50 women and their particular heart rate. So instead of having 5 women this time, I've gone with 50. So what I'm going to do now is actually introduce the formula on each side here. And it's something I tend not to do so much on this channel because I don't like formulas for the sake of them. But here they're actually quite instructive as to what's going on. So let's first focus on the mean side of things. You can see we have x bar plus or minus something, right? And so clearly we're going to construct this confidence interval such that it goes plus a little bit and minus a little bit from the actual sample mean, whatever that happens to be. And in this case, we actually find the sample mean to be 75.9. That's the average of the 50 women in the sample. So what's this T, S, and root N stuff? Well, I might start with the S. S is actually the sample standard deviation. So that is some indication of the spread of the underlying data. So the greater the variation in the sample's heart rates here, the greater this number will be in the numerator. So in other words, the greater the interval we will create will be. And that kind of makes sense. The more uncertainty we have in our sample, the more uncertainty we will have in the construction of our confidence interval for the population mean, right? Now the second thing we can see here is this divided by root n. And so quite simply, this tells us that more observations we have in our sample, the smaller this interval is going to be, right? Because as the denominator increases, this interval is going to decrease. Now you should find that somewhat understandable because the more people we have in our sample, the more likely the sample mean will be close to the true population mean, right? So that's going to reduce our uncertainty. And that all kind of makes sense, but what is this T doing? Why do we have this T figure here? So that's where we might want to consider the actual shape of this distribution. Think of it this way, we have a sample mean of 75.9. That's what we got from this sample if you averaged out this final column. And because there's 50 observations here, we'd be likely to get a population mean. The true value of the population mean should be somewhere near 75.9. The further we get away from 75, the less likely we're probably going to find our population mean. So we might say this has a normal distribution. Now the unfortunate thing is that it's not quite normal. It's actually what's called a t-distribution. And I'm not going to get into the t-distribution here. You can check out my video on the t-distribution if you like. But for the sake of this video, we'll just say that the t-distribution describes this bell curve shape for our possible values of mu. So what we need to do now is find this particular point on the t-distribution that encloses this 95% region. Now we're going to use 95% just as a rule of thumb. It's a nice round number and it gives us a good coverage for the potential values of mu. But don't be confused, this is just a arbitrary value. You can find a 96% confidence interval if you like, a 98.3% confidence interval, but we use 95 often because it's just nice and round. So to find this value, we're going to need to use this t-distribution, and the correct Excel formula to use to find it would be this here. You can go equals t.inv. This gives us the value on the x-axis here for a given probability. Now, when I say probability, I mean the amount of the distribution to the left of a given point. So it is a little bit confusing, but for this point up here, just think about it. If there's a 95% region between these 2 points, there's 2.5% in each tail, such that there's 97.5% below this value. So yeah, a little bit tricky, but 0.975 will get us this point. And then 49 is the number of degrees of freedom, which is always n-1. Again, I'll go into more details in the t-distribution video, which I'll link to in the description of this video. And that will provide for you the t value, and you can multiply then by s on root n. And finally, we can get our two confidence limits. 72.1 is the lower confidence limit. 79.7 is the upper confidence limit. So if we zoom over now to the proportion side of things, it's actually very much the same. In this case, the proportion of women that have a high heart rate was 0.12 because there was 6 out of the 50 people in our sample that had a high heart rate. Now have a look at this. This is the sample proportion, 0.12, plus or minus something, just like the previous example. It's just slightly different. It's clearly going to have something to do with P because it's now categorical data. So P is our proportion. And you can see that again, N is on the denominator. So this actually forms what's called the standard error when you have a binomial distribution. Again, I've got a video on that, but for the purpose of this video, we might just keep it simple and say this describes the uncertainty around our estimate. Now here we have a nice little z, which tells us it's going to be a normal distribution. Not a t-distribution in this case, but a normal distribution. But it's the same idea. We've got this kind of bell-shaped curve to our possible values for pi, for our population proportion. In other words, it's more likely for the population proportion to be something close to 0.12 than it is to be further away from 0.12. And no surprise, you can actually use Excel again to find this value of z. You can write equals norm.s.inv, and in the brackets, you're going to be putting 0.975. Why 0.975? Well, for the same reason we did on the t distribution. We're after the point above which lies 2.5%, so below which lies 97.5%. So it is a little bit confusing, but using this in Excel, that's the way we can find this particular value, and that happens to be 1.96. So then we can sub in all the values that we have, 0.12 being P, N is 50, and when you sub all those into the formula, you get 0.074 and 0.166. Feel free to confirm that for me. But we now have a nice 95% confidence interval for P. So how do we interpret both of these? Well, on the left side here, we can say we are 95% confident that the average resting heart rate for women is between 72.1 and 79.7 BPM. And on this side, we can say we're 95% confident that the proportion of women with high heart rates is between 0.074 and 0.166. So let's have a look and see some examples of confidence intervals you might find in academic papers and the like. This one is coronavirus related, and in fact, this paper came out just last week. Disparities in coronavirus reported incidence, knowledge, and behavior among US adults by Olson et al. And you might find in the results things that look a bit like this. African American respondents were 3.5 percentage points more likely than white respondents to report being infected with COVID. Now, after 3.5 percentage points, you can see we have a 95% confidence interval, 1.5 to 5.5 percentage points. So that's often a way that they will show confidence intervals in text. And you can see there's quite a few more of them as you go down here. This is the same paper, and this is a way that they've actually shown it using what's called a forest plot. So you can see that, for example, this is the probability of having COVID-19. We've got white people being the reference. This is from the USA. Now, black people have a higher probability of having COVID-19. And you can see that the estimate is this little dot here, and this line, the whiskers on each side, provide the 95% confidence interval. And that tells you down the bottom that it is, in fact, a 95% confidence interval. So it's quite crucial here to look down and see which of these confidence intervals cross this dotted line and which of them are wholly on one side of the dotted line. So here this tells us there's a significant difference between black and white people in terms of their probability of having COVID-19. There's not a significant difference between white and Hispanic because you can see that confidence interval crosses this line where the white people were at. So there's also a big difference between females and males, and that's a statistically significant difference as well. So that's quite neat. Other examples might be in graphical form, and for this I'm actually giving you some statistical stuff that I've been involved in myself as a biostatistician here in New South Wales. So this first one comes care of Health Stats New South Wales. And you can see here we have the proportion of Aboriginal people and non-Aboriginal people that are overweight, obese, or overweight or obese. So we get a nice comparison between Aboriginal and non-Aboriginal. But we also get these nice little confidence interval bars here, or they're also sometimes called error bars. And there'll be 95% confidence intervals for each of them. And quite telling, you can see that the confidence intervals for Aboriginal people are larger than the confidence intervals for non-Aboriginal. But that's only because we have a smaller number of Aboriginal people in our sample. So remember how the number of observations affects the confidence interval width? Well, in Australia, there's a lot more non-Aboriginal people than there are Aboriginal. So that's why these confidence intervals are a lot smaller. And finally, here's another way of showing confidence intervals in a paper that I've put together some years ago now. It's a bit old, but the funnel plot is a classic way of showing confidence intervals. Here we have the number of hip fracture procedures done per year. So each of these dots are hospitals in New South Wales. And on the y-axis here, we have the percentage of the procedures resulting in death within 30 days. So we've got the average for New South Wales, 7.35%. That's our mortality rate. And so as the number of hip fractures increases, you can see that the confidence interval is actually going to decrease, again because of the increasing value of n. So it's a nice way of seeing which particular hospitals are outside the bounds of these confidence intervals. So this hospital here is doing much better for its number of hip fractures done per year than we might expect. Anyway, there are some examples of confidence intervals you might see, as I said, in the wild. All right, so let's move on now and have a look at the sealed section for maths nerds. Yes, here we're going to have just a brief look at the difference between frequentist intervals and Bayesian intervals. Now, if you want to go deep into the difference between frequentist and Bayesian statistics, I've got a video that deals with this in depth, but I didn't want to make this video too long, so I'm just having a cursory overview of the differences here. But nonetheless, they are different. For frequentists, they will call these intervals confidence intervals, and for Bayesians, they're called credible intervals. But let's have a look and see how they differ. So from a frequentist perspective, theta, which is our parameter that we're trying to estimate, we consider that to be fixed, whereas the sample is something which might be considered random. This is the way that people tend to talk about frequentist intervals, and Bayesian intervals are kind of the reverse, where they say that theta is random, this is our parameter, is considered random, and the sample is considered a fixed singular item. Now that's just a simplification, and while I'm not going to get into really the weeds here, it's probably a good way of looking at it for the purpose of this video. So, for example, when I say on the frequentist side that theta is fixed, what I mean by that is that there's one kind of godly value of theta, and you can see that this first red bar might be a 95% confidence interval we've generated from a sample, and it crosses the true value theta. Now what frequentists would say would be that this sample is just a random outcome that could have been anywhere else. It could have been this sample we took here, or maybe it's this one, or maybe we could have taken this sample over here and this one's actually not including theta in its range. But the idea here is that 95% of these intervals we'd create, if they're of course 95% confidence intervals, 95 out of 100 of these would contain theta, and 5 out of 100 of those would not contain theta, like this one here. So this is the way we'd interpret a confidence interval. You'd say 95% of similarly constructed intervals would contain theta. Now again, the key point was that theta is fixed and kind of godly. I like that term godly because it means like it just is one particular value. Bayesians are a bit more flexible. They will attribute to theta a probability distribution. And in fact, they do this before they even see the sample. It's something called a prior distribution. So in this case, this is just a uniform prior in that they're saying that theta could be any number along this particular number line of equal probability between these two values. Then what happens is you get an actual sample mean, which might be somewhere here, and all of a sudden we can construct what's called a posterior. So this incorporates now information from our sample, and we construct again a probability distribution for theta. This time it's called the posterior. So you can see here that theta is considered like a random variable. It's given a probability distribution within itself, whereas the sample is only considered by itself. We don't have numerous theoretical samples here. We only have one sample, and from that distribution we create for theta, we can construct a 95% interval. So between these 2 points, you would have 95% of the data. And there we might say that there's a 95% chance that the interval contains the true population mean theta. Now it's quite interesting because in the intervals we've created so far in this video, and indeed in most of your textbooks, they'll be frequentist intervals, but they'll tend to provide you with the Bayesian interpretation of those intervals. You'll say there's a 95% chance that the interval contains the true population mean theta. But in reality, this is the technically true conclusion you can draw. So there's a bit of poetic license here in that we allow ourselves just this nice interpretation for using a frequentist interval, when in reality, hardcore statisticians will be wagging their fingers at us, because frequentist and Bayesian intervals, while they're often the same, there are situations where they are not the same. And I'll investigate that more in the frequentist versus Bayesian statistics video, which I'll put a link for in the description. But that, my friends, is the end of confidence intervals. Thanks so much for watching, and if you want to watch any of the others, you can check out the links below. My name's Justin Zeltzer. If you've got any comments, feedback, questions, feel free to shoot me an email. You can navigate to my address on the website zedstatistics.com. And keep an eye out on the YouTube channel, because I've got some interesting things coming up in the next few months. Keep subscribed and hit the notification bell to keep updated on that. But I'll see you next time.